values higher than the pore pressure are going to be called overpressure. All right. So let's try now to understand this source of overpressure. And the main phenomenon here that it's responsible for overpressure is the low permeability of the formation. And let's see how we can understand and calculate that. We're going to first make a case without overpressure. Okay, we have sediments in which the pore pressure is hydrostatic. This is the pore pressure, and the vertical stress increases with depth. What happens to effective stress with depth in this case? It clearly increases monotonically, right? Here it's 0, and as you go deeper and deeper, it always increases. Now let's try to think about if we have here it's all the same rock, and I want to plot porosity of the rock. What would you expect that porosity to be for that effective stress? So effective stress is increasing with depth. What is porosity going to be? It's going to decrease, right? And how is it going to decrease? It's going to decrease linearly. It's going to decrease with the curve. It's going to be like convex, concave, line. What do you think? If it would be linear, then we could solve it with linear elasticity, but unfortunately it is not. You have a... Why?
Because even if like all the particles are like close together due to their geometrical shape, there's always going to be some space in between.
Okay.
There's like a limit to how much.
Okay, yeah, I like that idea. So there is a point in which it doesn't matter how much stress you add, it's going to compress less and less, right? So this is going to look something like this. And probably, let's just put a number for an example here. This is going to be, sometimes on the seafloor, you find very high porosities, like 0.6, like 0.8. I don't know if you guys ever played in a lake close where the water comes in, but if there is mud that accumulates close to the entrance, you can, it's mud. You can go walk on it. It's very soft, very high porosity. And it's the same thing in the seafloor if you have lots of clays. But as you go deeper in this case, the porosity is going to decrease. This is what you would expect normally in this type of sediments. And I'm assuming in this case there is a significant amount of clay, and probably there's a little bit of sand, but there is a significant amount of clay. If that's the case, for this type of sediments, which usually in petroleum geology people call them mud rocks because they are made of clay, they are made of mud, and mud is made out of clay. We can write porosity with an equation that many times fits very well the behavior of this reduction in porosity with additional effective stress as an exponential equation depending on the vertical stress. So what this equation tells you is that if you know what is the vertical stress, which we know in this case, and if you know these two parameters, so these two are fitting parameters that very likely you may not know at the beginning, but you can take some samples, go to the laboratory, or do some correlations and calculate what those are. If you know this and you know those two, you know the porosity. So that's the case if you have an effective stress which always increases with time. But many times that's not the case. That's not the case. And as we saw before, and I'm going to do it again here, this is the surface of the water. We have now 2 layers of sediment. Our fish is always there. Now I'm going to have a sandy sediment. I'm going to have now clay here at the bottom. If I want to plot again, let me plot the hydrostatic pore pressure just as a reference. Seafloor effective stress is going to be 0, as we know. This is SV. And what's going to happen when we get to the clay if the clay didn't have time to compact? We're going to have overpressure, right? And if we have overpressure, this is going to be hydrostatic up to there. And when it gets over here, it's going to start to deviate. But now, let me show what's going to happen with something we didn't see before. What is the porosity? So we said that before, for this effective stress, we would expect porosity always to decrease with depth, right? But look, here, somewhere over here, it may decrease, okay? I'm going to delete this section because this is supposed to be sand, and this is just applicable to the mud rock part. So probably the porosity of the shale is going to be more or less the same as before. This is the trend, but then it's going to start to deviate. Why does it deviate? Look at effective stress. You can see that actually at this point the effective stress is higher than at that point. So your porosity, it may do something like this. Let me do it. I didn't also meaning to do that curve over there. But your porosity, instead of decreasing all the time, is going to deviate and is going to increase or not. It's not going to decrease as fast as you would expect. To our advantage, we can measure porosity, right? How do we measure porosity? So you lower logging tool, right? And what are the tools that we have to measure porosity? Density log. What else? Very well. What else? What about if the rock is filled with just with brine? We can also use resistivity, and we could also use P wave to estimate that porosity. All of those are going to give us indications about what the porosity is. And if we calculate the porosity of those and we find that there is an anomaly in porosity and porosity doesn't go down as we expect, that's because very likely there is an overpressure. So in problem number 3, you have to calculate pore pressure not based on hydrostatic pore pressure, but based on an anomaly of porosity. Okay? So how do you're going to do that? Here you have the table. You have depth. You have void mass density. For each of these cells, you calculate what is the vertical stress at that location. Okay? And from that vertical stress, you can calculate what is the, and with porosity, you can calculate what is the effective stress. If you know what is the effective stress, you can calculate the pore pressure. So let's try what I said. And let's do a little bit of math over here. Let me do it in another page. It's just some algebra. So this same equation is going to be like this. And what is always, this is going to be always the same equation. What is effective vertical stress? Can anyone tell me?
Vertical stress minus pore pressure.
Total vertical stress minus pore pressure, right? So we know that guy. We know that guy very well, okay? That's our best friend. And we know this one too because we measure that with our logging tools. And so this is the logging tool. This just comes from integrating raw bulk. We know these two also from the lab. The only unknown is going to be that. You see? So let's do a little bit of math. How would you solve for PP? Probably we'll pass this one to the other side. And what do you do after? Any suggestion for some points? Take a log. Which one? Natural log, right? So ln of this is going to be that. And now, let's see. We have the PP here. So the PP, we can pass it to the other side. And I'm going to have to divide by B. So wait. I'm trying to skip some steps here, but this is not working. So PP beta, that's going to be the PP beta, right? Is going to be logarithm, natural logarithm of this minus beta SV. So PP finally is going to be this. Right? Yes? This one? Let's see. So this one is plus, right? So, and this one is negative. I moved it over, so if it goes to the other side, yeah, it should be plus, right? Okay, I remember what happens here. Actually, let me change the order here. It's the same, okay? But Vedas V this guy is going to be negative. And because it is negative, it is going to be a positive number. And then that's going to give you the value of pore pressure. So that's how you solve for pore pressure when you have overpressure. You're going to do that in homework, okay? But something that you're not going to do in the homework is to solve a problem that kind of gives you an idea of how long it can take for this pore pressure to be dissipated during sedimentation process. And in order to solve that problem, we're going to solve an approximation of what is called the diffusion equation, which is let me repeat what we had before. I have water, I have sand, I have clay, and let's say that I have here a very impermeable rock. Okay? When I have sedimentation and these ones, all those sediments start to compress the clay, the water is going to try to move up and escape in that direction. Can you see that? So if there is water over here, it's going to escape very quickly over there. If there is something over there, because this is more or less impermeable, it's going to go, it's always going to have to go up. That distance is very important because the longer that distance, the longer it will take for the pore pressure to be dissipated. In order to solve that problem, there is an equation which is called the diffusivity equation. I'm going to write, but we're not going to solve, that tells us that the variation of pore pressure with time depends on the diffusivity parameter and the variation of pore pressure 2 times with space. So this is called the diffusivity equation for pore pressure. This parameter, which is the diffusivity parameter, hydraulic diffusivity, is going to be equal to the compressibility, the bulk compressibility of the sediment times the permeability. So look, the higher the permeability, which makes sense, the higher the diffusivity, divided the viscosity of the fluid. So the lower the viscosity of the fluid, the higher the higher diffusivity is going to be. So if you have a very low fluid viscosity, like for example a gas, then that's going to drain much more quickly than water or than oil, right? That makes sense. And in order, we're not going to solve completely this equation, but if we were to measure what is called the excess of pore pressure above the hydrostatic as a function of time. And as soon as we have a loading, we have this pore pressure to be somewhere over here. With time, the pore pressure is going to decrease, and that's why it's called pore pressure relief. And more or less at 2/3 of the additional overpressure, we are going to know that this time is going to be approximately the square of the drainage length, which is that one. And it makes sense. Look, the bigger the drainage length, the higher the time is going to take, divided the diffusivity parameter. So let's do one example to illustrate this concept. And you're going to need a calculator for this. And I'm going to give some extra points to whoever solve this first. Okay? So we're going to have case 1. We're going to find the time it takes for pore pressure to be dissipated in a sand. What is the typical permeability of a sand? Anyone can tell me what is a good permeability of a reservoir, of a sandstone reservoir? How many? 50 millidarcy? Yeah, 50 millidarcy is okay. Very permeable reservoirs have about 1 darcy permeability. So let's assume a typical fine sand with 100 millidarcy permeability. What's the permeability of a mud rock, of a shale, with lots of clay? Nanodarcies? How many nanodarcies? 25. That's a very, very tight rock. Like unconventional rocks, those have around that permeability, very tight. 10 nanodarcies, 25, 100 nanodarcies still is very tight. So let's assume 100 nanodarcy, okay? To help you with these calculations, I'm going to remind you that 1 darcy is 10 to the minus 12 meters squared. And I'm going to also tell you that the viscosity of water is 10 to the minus 3 Pascal per second. And we're going to assume that the compressibility of the rock is about the same. And M bulk is, you're going to get familiar with these numbers later on, but just believe me that compressibility is a relatively soft rock, and that's going to be 1 gigapascal. And the length of the layer that is subjected to overpressure is 100 meters. I want you to tell me what is this T star for the sand and for the shale. Okay? So you have everything you need in those equations. Let me know if you have a question, okay? So I said I will give points before to whoever told me, I don't remember what, but it was, but I remember who raised the hand. It was Miss, what's your last name? Yeah. Montero. Miss Montero, okay. And I think it was you over here. What's your last name? HSU. HSU. Miss, how do you pronounce that? Sue?
Yeah.
Mr. Sue. Okay. All right. after you compute these numbers, you realize that what is the magnitude of time that we're talking about that it can take.
Could you tell us how much pascals is in megapascal?
So a kilo is 1,000, a mega is a million, a giga a billion, so 10 to the 9, and a tera is 10 to the 12, right? So let me write. Where is my coffee? Actually, I'm going to drink that coffee. It's a good coffee, Brazilian coffee. So I recommend that you work in the SI system. So you put everything in the SI system and then just multiply and divide and you should get the answer. And you're going to get the answer in seconds, right? But if you tell me, oh, the answer is 8.6 to 10 to the 11 seconds, that's going to be kind of hard to understand what that is. So try to convert it to a meaningful unit that we can understand. Let me know if you have any question, okay? This is not an exam, so just feel free to ask me anything if you want. So it's very important you do the homework on your own, okay? I know that you may find some of this material from other classes, from other professors, or even from my same class. But you should try to do it on your own. You should try to practice. The only way to get good at something is to practice. And you don't try to run a marathon without practicing because that's not going to work. And it's the same thing with this. You don't try to go to the exam without practicing because it's not going to work either, even if it looks easy before. Yes? Probably not. Probably not. It looks that you're missing something there in your equation of t. No, it's okay. Oh, okay. So what is that d? No, but you cannot use Darcy with meters and seconds. You have to convert your Darcy's to meters squared. So over there. So a Darcy is a field unit. You cannot use that. You got the answer?
Is that right?
Mr. Wang? That looks about correct. So this is the sand, and that's the clay. Mr. Tozer, you have the same answer?
I have an answer.
Ran it through on the calculator, I agree.
Okay. Yes?
I have an answer too.
Okay. And you have an answer too? Anyone has also an answer? Okay, 5 more. Okay, I'll remember you guys, and then let's just wait a little bit that everyone solves the problem. We'll go through the answer. All right. Okay, let's see. What is the time for the sand?
100,000
What?
seconds.
Seconds? 100? No, 1,000, you said? 1.1 day. Okay. Yeah, you see, I got, I didn't get that time at the very beginning. So 1.1 days, right? Which is relatively fast, right? We're considering 100 meters formation. You put load on top. The pore pressure can relieve very quickly, just in 1 day. What about the shale? What is the number for the shale? What's your name? Paul, what?
I got 3,000 years.
3,000 years? Is that what you got, guys? 3,000, more or less? So something very important, and I think